Anesthesia Machine and Breathing Circuits by Dr. Islam Bardan, Lecturer of Anesthesia and Surgical Intensive Care, Alexandria University. Learning objective is to explore the major components of anesthesia machine, either internal or external. This is a picture of anesthesia machine from front view and back view. From front view, you can see what is called flow meters. You can control it with flow controls and a vaporizer system switch to turn it on and off. Gauges for pressure, primary and secondary. Primary gas supply gauges, usually measuring pressure coming from pipeline, and secondary gas supply pressure gauges for cylinder. We have auxiliary oxygen flow meter, a display here, suction regulator, bellows assembly for mechanical ventilation, breathing system composed of rebreathing bag, carbon dioxide absorber here, oxygen flush button here. From back view, you can see electrical outlet with circuit breakers, main circuit breaker, also oxygen power outlet, waste gas receiver, back cover, scavenging connector, cylinders, cylinder yokes, and pipeline inlets. Maybe it is complicated, but we will demonstrate all of these parts over the next slides. Another more complicated diagram showing the basic parts of the anesthesia machine. Section A with cylinder of nitrous oxide and oxygen with the check valves here. Cylinder pressure gauges, pressure regulator. Another section B with pipeline supply of nitrous and oxygen with the check valves and gauges. Fail-safe valve with oxygen supply failure alarm. Another second stage oxygen pressure regulator. Oxygen flush valve. Section C with flow meter and the flow control valve, vaporizers, check valve, and common gas outlet. We will discover these parts over the next slides. We can divide it into supply of gases, means of controlling measuring gas flow, means of controlling measuring pressure, vaporizers, breathing system, means to ventilate patient, scavenging system, safety devices, and monitors. For supply of gases, either oxygen, air, nitrous oxide, it can be piped medical gas supply from central depot or cylinders on machine as mounted in the picture on the back of the machine. As a mean for controlling and measuring gas flow, we have what is called flow meters. As a mean for controlling and measuring pressure, we have pressure gauge and pressure reducing valves. Vaporizers. Breathing system can be circle system or open systems like Bain and Ayre's TBs. To ventilate our patient, we have reservoir bag for manual ventilation or ventilator for intermittent positive pressure ventilation. Also scavenging system and safety devices and monitors. All of these parts are integrated in a common system connected to hospital information management system and the monitors to ventilate our patient and give him anesthesia safely. So we have a source for gas supply from cylinder or pipeline to gas inlets, pressure reduction, flow meters, vaporizers to common gas outlet connected to breathing circuits through airway and patient. Breathing circuits are connected with ventilator, scavenging system, and safety devices, also connected to monitors. All of these parts of the anesthesia machine and the anesthesia tower or anesthesia workstation are integrated to anesthetize our patient safely. First, supply of gases. Again, it can be a piped medical gas supply from central depot, either with cylinders like here, nitrous oxide cylinders, oxygen cylinders, or oxygen tank. All of this piped through here, above here, to OR recovery units, ICU, with oxygen backup cylinders here. So it's a pipe system, start from here and distribute to all parts of the hospital requiring manipulation and uses of medical gases. Another source, which is the cylinders mounted on the back of anesthesia machine, like here. Means of controlling, measuring gas flow. Flow meter. Flow meter consists of a tapered glass tube containing a bobbin. This one is a bobbin or ball which floats on the stream of moving gas. As the gas flow rate increases, the float is carried further up the tube and so indicating flow rate. Like here, this is the oxygen flow control. This is the oxygen flow meter. As the gas increase, flow increase from 1 to 2 to 3 liter per minute. Specifically constructed for each gas: oxygen, nitrous, air. For controlling and measuring pressure, we have what is called pressure gauge. This measures the pressure in the cylinder or pipeline. The pressure gauges for oxygen, nitrous oxide, and the medical air are mounted in a front-facing panel on the anesthetic machine, like here. For pressure regulation, we have what is called pressure regulator or reducing valve, pressure reducing valve. Gas and vapor are stored under high pressure. A regulator reduces the variable cylinder pressure to a constant safer operating pressure. Otherwise, high pressure coming from the cylinder can be a reason for machine destruction. Vaporizers, another important part of the anesthesia machine. A vaporizer, like here, for sevoflurane or isoflurane mounted on the anesthesia machine beside the flow meter. Below are the gauges for pressure measurements. A vaporizer is designed to add a controlled amount of an inhalational agent after changing it from liquid to vapor. The function of this is to change anesthetic, which is liquid, to a vapor, so it is called a vaporizer, and add it to fresh gas flow coming from the flow meter here in this way. This is normally expressed as percentage of saturated vapor added to the gas flow. You can see graduation on the top of the vaporizers, 1, 2, 3%, and so. Breathing circuits function to deliver oxygen and the anesthetic gases to patients and eliminate carbon dioxide. This is the function of a breathing circuit, which is connected to common gas outlet of the anesthesia machine. This is the way to deliver oxygen and the anesthetic gases coming from vaporizer to patients, and the way to eliminate carbon dioxide. Every circuit has certain components. Fresh gas flow outlet connected to the breathing circuit, tubing to direct the gas flow, an adjustable pressure limiting valve to control pressure within the system and allow scavenging of waste gas, a reservoir bag to store and assist with ventilation. Circuits can be classified according to the method of removing carbon dioxide. Maybe carbon dioxide is eliminated by washout from the circuit. So I will depend on gas flow to push carbon dioxide out of the circuit. So patient will not rebreathe his expired gas. So it is non-rebreathing circuits like Bain system and Jackson-Rees system, and we will see. Another type of circuits depend on soda lime, a material added to the circuit to absorb carbon dioxide. So it is carbon dioxide absorption circuits. The patient will rebreathe his expired gas. So it is a rebreathing circuit. It is a circle system. Circle system. A circle system improves the efficiency of anesthetic gas delivery by recycling gas that is expired from the patient and thus reducing the amount of fresh gas flow required. Like here, we will see. Fresh gas flow leaves the anesthetic machine and passes to the patient, okay, here, through one-way valve, which allows flow of gas only in one direction. To the patient, expiration again. As expiration occurs, the exhaled gases from the patient will pass through another one-way valve to the adjustable pressure limiting valve, then to reservoir bag or ventilator. Again, here, before this expired gas is mixed with fresh gas flow coming from here, it will pass through soda lime, which absorb carbon dioxide. And again, this gas will be mixed with fresh gas flow and again to the patient. It is a closed system. The patient is allowed to re-inspire the gas mixture that he expired again and again. But we have issues must be addressed here. First, to compensate for the oxygen consumption by the patient, the fresh gas flow of oxygen will be added to the system, 2 to 3 liters per minute down to 250 ml per minute, which met the basal metabolic rate, and it is a closed circuit. Second, to eliminate the carbon dioxide produced by the patient, expired gas will pass through soda lime, which absorbs carbon dioxide. This is a canister of soda lime attached to the machine here. Soda lime is one of the most important components of the circle system. It is a mixture of calcium hydroxide 80%, sodium hydroxide 4%, and water 16%. It contains a pH-sensitive dye, which indicates when the granules are exhausted. It is a reaction between carbon dioxide and soda lime with heat production, so it is exothermic reaction, and water production. You should know signs of exhaustion. First, inspired and end-tidal carbon dioxide, as demonstrated on the capnography, which is a monitor connected to the patient, exceeds a known threshold. The granules will change in color. Signs of elevated inspired carbon dioxide can be detected later, like rise, later fall in heart rate and blood pressure, hyperpnea for patient spontaneously breathing, dysrhythmia flushing, sweating, respiratory acidosis on blood gas analysis, increased bleeding at surgical sites. Like everything, we have advantages and disadvantages. Regarding advantages of the circle system, constant inspired concentrations. It maintains and guarantees a constant inspired concentration of inhalation anesthetics. Conserve respiratory heat and humidity by production of water and heat during reaction with carbon dioxide, which is valuable for the patient. It is useful for all ages. Useful for closed system and low flow. It helps to reduce anesthetic gas use, so more economic and prevent operating room pollution. Regarding disadvantage, it is a complex design with risk of malfunctions of unidirectional valves with carbon dioxide rebreathing and with increased dead space. Also, because of this complex design, there is risk of disconnection, risk of misconnection, obstruction, or leak. It can be used in children, but high resistance. Two examples for circuits are Bain circuits, our Bain system, and Jackson-Rees modification of Ayre TBs. Bain system is a coaxial circuit in which fresh gas flows through an inner tube, like here, which is inside the outer corrugated tubing. The aim is to warm the fresh gas going to the patient by the expired gas flowing in the outer tube. Exhaled gases from the patient enter the outer corrugated tube and will be vented through the expiratory valve here, near the reservoir bag here. So fresh gas flow is coming in this way to the patient, expiration in the outer tube, to the valve and to the bag. We have a volume recommended of fresh gas flow to prevent rebreathing. Remember, this type of circuit, carbon dioxide elimination, will depend on the fresh gas flow. So, during spontaneous breathing, I need 2 to 3 times minute ventilation of the patient, like 100 to 150 ml per kg. But for controlled ventilation, we need from 1 to 2 times minute ventilation, around 70 ml per kg. So it is more efficient and most efficient for controlled ventilation, but not recommended for spontaneous breathing. Jackson-Rees modification of Ayre TBs. This is the circuit, tubing, bag, no valve but opening here, connected to fresh gas flow from here and connected to patient from here. No valves, so offers minimal resistance to gas flow. Breathing bag connected to the end of the breathing tube to allow controlled ventilation and scavenging. This bag here is the way for scavenging of expired gases, and through this opening we can control the opening here, and it likes a valve to control the pressure inside the system. And I can use it for ventilation manually. It is commonly used for pediatric patients and transportation. A volume of fresh gas to prevent rebreathing again is recommended. During spontaneous breathing, it is 2 to 3 times minute ventilation. During controlled ventilation, it is 2 times minute ventilation. Fresh gas flow below the recommended will be a reason for rebreathing and increase the carbon dioxide. We have different means to ventilate patients, either reservoir bag, like this, or mechanical ventilator, like this. This is an example of mechanical ventilator built inside the anesthesia machine trigger focus. You can see here different modes of ventilation like volume control, pressure support. This is a monitor here for tidal volume and the frequency and the minute ventilation, beep, plateau pressure and peak pressure. It is a nice machine. Ventilators may be integrated within the anesthesia machine or configured later. These are often electronically controlled and pneumatically powered. Traditionally, anesthetic machine ventilators have had a minimal number of controls. The anesthetist could vary minute volume by setting tidal volume and ventilatory frequency directly, or by adjusting inspiratory time, inspiratory flow rate, and ratio of inspiratory to expiratory time. The newest models resemble critical care ventilators in their capabilities. These may perform self-test upon startup, volume or pressure-controlled ventilation modes, assisted spontaneous ventilation, and electronically adjustable beep. Last to know is the scavenging system. Aim to vent out the exhaled anesthetic vapors and maintain a vapor-free operating theater environment. Here, scavenging can be connected to the ABL valve or to the ventilator. We have safety devices like anti-hypoxic device, fail-safe valve, oxygen flush control, and Ambu bag. Anti-hypoxic device. Modern machines have interlocked oxygen and nitrous oxide flow controls. So the aim is to balance between what is given to the patient in case of using nitrous oxide. The purpose of this device is to cut off or proportionately decrease nitrous oxide in case oxygen pressure is lost. This prevents inadvertent delivery of a hypoxic inspired gas mixture, as the ratio of oxygen to nitrous oxide concentration never decreases below 0.25. Another device, which is fail-safe valve, it ensures that whenever oxygen pressure is reduced and until flow stops, the set oxygen concentration shall not decrease at the common gas outlet. In addition, the loss of oxygen pressure results in high priority alarms, audible and visible. Oxygen flush control is a device to allow direct communication between the high oxygen pressure circuit and the low pressure circuit. When the oxygen flush button is depressed, the oxygen flush valve will open and deliver 100% oxygen flow of 35 to 75 liters per minute to the breathing circuits. So it bypasses all pressure reducing valves in the circuit. Manual resuscitator, Ambu bag, very important to know. It is a backup in case of failure of anesthesia machine. It is commonly used during resuscitation. Very important device. This is the basic components of a manual resuscitator. It's a silicone bag with a reservoir bag, oxygen inlet tube, pressure limiting valve, patient valve connected here to the patient. Expiration is from here. Again, another diagram with two non-rebreathing valves here. Expiration port, source of oxygen, and the connection to reservoir bag filled of oxygen. We will see the mechanisms of manual resuscitators. During inspiration, here, when the bag is squeezed, on the proximal side, close to the patient, the diaphragm here will be seated against the exhalation port. This is the exhalation port, interrupted line here, and this is the diaphragm. During squeezing of the bag, this diaphragm will be seated against the exhalation port. And a fish mouth portion of the valve, this is the valve, which is a non-rebreathing valve, open. So by this way, the valve open and the ports here close, so I can ventilate the patient. In the same time, during inspiration, on the distal side, away from the patient, there is another non-rebreathing valve, which is the bag refill valve. This valve during inspiration closes, and the oxygen delivery tubing from here will flow into the reservoir tubing, so it can be filled. During expiration, the bag self-expand. It is made of silicone. During this time, here, on the proximal side, close to the patient, the fish mouth closes. It is opened here, but here it is closed. And the flap falls away from the exhalation channel. So exhalation can happen from this direction and like this. From this direction from the patient and outside through the port. In the same time, on the distal side, away from the patient, the other non-rebreathing valve, which is the bag refill valve, opens, and the bag fills when the oxygen from the delivery tubing as well as reservoir tubing flows into the bag. Monitors are very important part from the anesthesia workstation. Anesthesia units must incorporate certain minimum equipment related monitors. Monitors for airway pressure, volume of expired gas, inspired oxygen concentration, anesthetic gas concentration, physiological parameters may be incorporated into the machine. So it is connected to the machine. Monitors to measure patient physiological status like state of awareness, capnography, pulse oximetry, blood pressure measurements, either invasive or non-invasive, ECG. It is connected also to the machine and the mechanical ventilator as a safety to measure how much is the inspired concentration of oxygen, carbon dioxide, gases, expired concentration. Also for the action and function of the ventilator like pressure and volumes. Again, the complicated picture again. I hope it is clear for you now. Thank you.